Welcome to our deep dive into how our brains learn. It's pretty amazing how every new skill or memory, every thought even, is a physical change happening in your brain. The scientist who really cracked this open was Donald Hebb.
Yeah, his 1949 book, The Organization of Behavior, was a total game changer.
So before we jump in, what was the scientific landscape like when Hebb was doing this work?
Well, he was trying to figure out how individual neurons lead to those really complex behaviors we see.
But didn't they even have all the tools we have now?
Nope, not even close. It was way before things like, advanced brain imaging and all those genetic tools we use now.
Wow, so that must have been a huge challenge.
Oh, absolutely. He was basically working in the dark, but even without those fancy tools, he came up with this theory that still holds up pretty well.
And what was the core of his theory? How did he explain how neurons create behavior and learning?
He proposed that it all comes down to the way neurons connect and interact with each other. He introduced this idea of cell assemblies.
Cell assemblies. So what are those?
Well, think of it like a network of lights. You flip a switch and a specific pattern of lights turns on.
Okay, I'm following. So how does that relate to neurons?
When you experience something, a particular group of neurons in your brain activates, just like those lights turning on. And that specific group, that's your cell assembly. It's like a neural representation of that experience.
So for every new thing we learn, a new cell assembly is created.
That's the idea. But it's not just about them turning on, it's also about how often they fire together. Hebb thought the more those neurons fire together, the stronger the connections between them become.
I see. So that makes it easier for them to fire together again next time, right? Even if the trigger, the stimulus, is weaker.
Exactly. It's like, walking through a forest. The more you walk a certain path, the more defined it becomes, easier to follow. Same thing with these neural pathways.
So that brings us to the probably the most famous phrase in neuroscience: cells that fire together wire together. I mean, is that directly from Hebb?
He didn't actually say it quite like that, but that phrase really does sum up his idea perfectly. And it also ties into what we call synaptic plasticity.
Okay, break that down for me. What is synaptic plasticity?
So the synapse is that tiny gap between two neurons, and that's where the communication happens. And Hebb's idea was that when two neurons fire together a lot, that synapse, it gets more efficient. Like that path in the woods again, the more you walk it, the easier it is to travel.
Okay, so it's like those neurons are building a stronger connection each time they fire together, like laying down a new highway in the brain.
You got it. And this whole process, the strengthening of connections, that's Hebbian learning. And it's at the core of how our brains learn and adapt to, well, pretty much everything.
I mean, it's just one phrase, but that really does have huge implications, right? It's not just a catchy saying. It's like this fundamental rule of neuroscience.
Oh, absolutely. It's been backed up by tons of research since then, and it helps us understand things like how memories are formed, how we learn new skills, you name it.
When we talk about learning, it's so obvious that kids learn differently than adults. Do Hebb's ideas address that too?
They do. He proposed that there are actually two stages of learning.
Two stages.
Yep. Primary learning, which happens mostly during childhood, and then adult learning.
So what's the difference between the two?
Think about it this way. Primary learning is like building the foundation of a house. It's about establishing those basic neural representations, those fundamental cell assemblies.
So like babies and little kids are creating all those basic neural pathways that they'll use later.
That's right. And it's a gradual, slow process, like laying down those foundational bricks one by one. Then adult learning is more like building upon that existing foundation, adding rooms, maybe a second story.
Ah, I see. So we're using those existing neural pathways, those cell assemblies, and making connections between them to learn more complex things.
Precisely. And this is part of why early childhood experiences are so important. They're like setting the stage for all future learning.
Okay, so we're seeing how this applies to learning and brain development. But how did Hebb's work affect other fields, like psychology?
Well, before Hebb, a lot of psychology was focused on like simple stimulus and response. It was all about how external stuff triggered behavior, like a simple input-output model. But Hebb showed that there's more to it than that.
Right, it's not that straightforward. So he brought in the brain itself, the internal processes, into the equation.
Exactly. He showed how those internal brain processes, especially the formation and strengthening of those cell assemblies, were crucial for shaping behavior.
So he kind of like shifted the focus from the outside world to the internal world of the brain.
Exactly. And that was huge for paving the way for cognitive psychology. That's all about understanding mental processes, like memory, attention, perception, that kind of thing.
Wow, so Hebb's ideas really did bridge the gap between behaviorism and cognitive psychology.
And his influence didn't stop there. His work also had a huge impact on the field of artificial intelligence. Actually, his idea of cell assemblies, that was a major inspiration for creating artificial neural networks.
Hold on, so the algorithms that power, like facial recognition software and self-driving cars, they were actually inspired by how our brains learn.
That's right. Which, I mean, that speaks volumes about how powerful and relevant Hebb's ideas still are today. He was working with a very limited understanding of the brain back then, but he came up with this theory that has really stood the test of time.
It's amazing. And it seems like this whole concept of cells that fire together, wire together, has really gone way beyond what Hebb could have even imagined.
Oh, totally. And as we continue to learn more about the brain, that relevance just keeps growing. It's helping us understand the brain's capacity for change and adaptation in all sorts of ways.
It's like we're looking at the world in a whole new way now, thinking about our own experiences in terms of these neural connections forming and getting stronger.
And that's the beauty of neuroscience, right? It gives us this amazing window into how our own minds work, and we can start to appreciate how amazingly complex and adaptable the human brain is.
So what else? What are some of those more surprising or counterintuitive things we've learned from Hebb's work?
One that's super fascinating is the role of inhibition in learning. Turns out, it's not just about neurons firing together.
What do you mean?
Well, sometimes learning also involves certain neurons being, like, silenced or inhibited.
So it's like sometimes to learn something new, you need to unlearn or forget something old.
You could think of it that way. It's like pruning a tree, you know? You got to cut away some branches so the others can grow strong. The selective inhibition is super important for shaping the brain's response to new experiences.
And it makes sense, right? If everything was constantly getting stronger, our brains would be, I don't know, overloaded or something.
Right. It's like our brains are constantly fine-tuning themselves, making some connections stronger, others weaker, to create these super efficient neural networks.
So there's a lot more going on than that simple phrase, cells that fire together, wire together, let's on. It's way more complex.
Oh, yeah, way more. And that's what makes neuroscience so exciting, right? There's always something new to discover. Every layer we peel back just reveals more and more complexity and nuance.
I can't wait to hear more. But we'll have to pause here for now and let our listeners catch their breath. Be sure to tune in next time for part 2 of our deep dive, where we'll explore some even more surprising aspects of Hebb's work and how his ideas are still shaping the world of neuroscience today.
One of the most interesting things about Hebb's work is how it helps explain the phantom limb phenomenon.
You mean where someone feels sensations, like pain even,
Yeah.
in a limb that's not there anymore?
Exactly. And for the longest time, that was a real head-scratcher. Like, how could the brain create feelings in a limb that's gone?
Yeah.
But Hebbian learning actually offers a possible explanation.
Okay, I'm intrigued. How does that work?
Well, think about it. Before the limb was lost, all the neurons representing it were firing together all the time, right? So their connections were super strong.
Makes sense.
So even though the limb's gone, those neural networks, they're still there in the brain. And sometimes they can get activated, maybe by activity in, like, nearby areas of the brain. And that can cause the person to actually feel things in that missing limb.
So it's like those pathways are so strong, so ingrained, that they kind of linger even when the physical limb is gone. Wow.
It is kind of airy, right? But it shows how incredibly plastic the brain is, you know, how it rewires itself based on experience.
But that rewiring isn't always perfect, is it?
Nope, not always. Sometimes those pathways lead to some unexpected or even unwanted results, like phantom limb pain.
Makes you wonder how else that rewiring might show up. Like we were talking about the differences between how kids and adults learn. Does Hebb's work have anything to say about why those early experiences are so important for development?
Oh, definitely. Hebb was big on the idea that primary learning, the kind that happens in early childhood, is like setting the foundation for everything else. During those early years, the brain is crazy plastic, making new connections super fast.
It's like more adaptable then.
It is. Think of a sculptor working with clay. It's easier to mold and shape while it's still soft, right? Same with the brain.
So those early experiences are literally shaping the physical structure of a child's brain.
Exactly. And that's why those early experiences are so crucial. We're talking about shaping the very structure of the brain, those neural pathways they'll use for the rest of their lives.
Makes you realize just how much impact things like, poverty or neglect can have.
Yeah, it's heavy stuff. Research actually shows that kids who experience that kind of adversity early on, they often have changes in their brain structure and function.
Which can lead to problems later on.
Yeah, like with learning, behavior, emotional regulation. It's tough.
But that also shows just how important early intervention is, right? If we can provide support, create those good experiences, maybe we can help offset some of those negative effects.
Absolutely. It's never too soon to start nurturing those young minds. Give them the opportunities they need to do well.
It's powerful stuff. But so it sounds like even though early experiences are super important, it's not like everything's set in stone after childhood.
Right. The brain keeps its plasticity throughout life, thankfully. We can keep learning, keep growing, making new connections, rewiring things, even as we get older.
So there's still hope for us old dogs to learn new tricks.
Exactly. And that actually goes back to what Hebb said about stimulation. He thought we're basically wired to seek out new experiences, to challenge ourselves mentally.
We crave it.
We do. And he thought that drive, that need for stimulation, is actually what keeps the brain active, keeps it plastic, so we can keep learning and growing throughout life.
So our brains thrive on novelty, on challenges. We're not meant to just sit back and relax once we hit a certain age.
Not at all. Hebb thought that constant interplay between the brain and the environment, that back and forth, that's what keeps us mentally sharp, keeps us engaged.
So we should all be trying to learn new things throughout life.
It's a good idea, whether it's learning a new language, taking up a hobby, even just having those thought-provoking conversations, all of it helps.
It's almost like we have the power to shape our own brains to a certain degree.
Yeah, by choosing how we interact with the world around us.
That's pretty cool. But this drive for stimulation, does it ever go too far? Can we get too much of a good thing?
That's a great question. And Hebb actually thought about that too. He talked about optimal arousal, the idea that there's a sweet spot for stimulation, a level that's best for learning and performance.
So too little stimulation and we get bored, too much and we're overwhelmed.
Right. And that sweet spot, it can be different for everyone. Some people do great in high stimulation environments. Others need things calmer, quieter.
We all have our own limits. But how do you know when you've hit that sweet spot?
Well, there's no magic formula, but Hebb suggested that when you're at that optimal level, you feel alert, focused, engaged, but not overly stressed or anxious.
So it's like a balance.
Yeah.
Challenged, but not overwhelmed.
Exactly. It's like finding that flow state where you're completely absorbed in whatever you're doing.
And finding that can really help us learn and perform better.
It can. It's about paying attention to how you respond to different levels of stimulation and then adjusting your environment, your activities to match.
This is all making so much sense. Hebb wasn't just a brilliant neuroscientist. He was a sharp observer of how people behave, too. Our brains are always searching for that balance, that sweet spot.
He really was a pioneer, bridging the gap between, the biological and the psychological, showing how our brains are literally wired to interact with the world in such a dynamic way.
Amazing. I feel like we could keep going on this forever.
There's always more to explore.
Well, on that note, I think it's time for us to move on to the last leg of our deep dive. It's incredible how much ground we've covered, from those basic cell assemblies to optimal arousal and everything in between.
I know, right? And what's really exciting is that Hebb's work isn't just about the past. It's really shaping the future of, fields like neuroscience and even artificial intelligence.
So let's talk future then. How is Hebb's work influencing that cutting-edge research, especially in neuroscience?
Well, one area that comes to mind is brain-computer interfaces.
Wait, those things that let the brain communicate directly with devices? Sounds like sci-fi.
It does, but it's becoming more real every day. Researchers are working on brain-computer interfaces that could, for example, help people who are paralyzed regain control of their limbs.
Just by thinking about moving.
That's the goal. And Hebbian learning, that's a big part of how that learning process would work. The brain has to learn how to control that external device.
So it's like the brain's learning a new skill, like learning to play an instrument or something. But instead of controlling muscles, it's controlling a machine.
That's a great way to put it. And that's just one example of how Hebb's ideas are helping create these groundbreaking technologies that could really change people's lives.
It really is mind-blowing. It's like we're entering this whole new era of neuroscience where we can not only understand the brain, but interact with it in ways we never thought possible. But what about AI? We talked about that a little earlier. How is Hebb influencing that field?
Well, we talked about cell assemblies being the inspiration for artificial neural networks, right?
Right.
And those networks are now at the heart of so many AI applications like image recognition and language translation.
It's almost hard to wrap your head around. Our understanding of how the brain learns is being used to create machines that can learn too.
Yeah.
What are some of the potential benefits and, I guess, even the risks of that kind of technology?
Well, the potential benefits are huge. AI has the potential to change so many things, like healthcare, transportation. Think about automating tasks, making things more efficient, even leading to new discoveries.
Like AI that can diagnose diseases maybe even better than humans can.
Exactly. Or AI that can, design new materials with properties we never even thought of. The possibilities are pretty much endless.
It's definitely exciting to think about all the good AI could do, but I also can't help but think about the potential downsides too. What if those machines get too smart? Could they become a threat?
That's a question a lot of people are asking, and it's an important discussion to have. The key is that as we develop more and more sophisticated AI, we also really focus on ethical considerations, safety measures, all that.
So it's not just about like advancing the technology itself, but making sure it's used for good and aligns with our values as humans.
Absolutely. And this is where Hebb's legacy can actually guide us. He was all about understanding the brain's mechanisms, not just copying its functions.
So we need to apply that same principle to AI. We need to understand how these systems learn, how they make decisions, not just be impressed by what they can do.
Exactly. It's about understanding the why behind the what for both the brain and the machines we're building.
That makes a lot of sense. So, thinking about those bigger questions in neuroscience, the mysteries that scientists are still trying to figure out, how does Hebb's work play into that?
Well, one of the biggest ones is consciousness, right? How does all that neural activity, those firing neurons, how does that create the experience of being aware, of feeling, of thinking?
So we can kind of explain how the brain processes information, but we still don't really understand what it feels like to be, well, us.
It's one of the ultimate mysteries. And while Hebb's work didn't directly address consciousness, his focus on how interconnected those neural networks are, that's given us a framework to think about how more complex stuff emerges from, simpler neural processes.
So even though he didn't have all the answers, he kind of laid the foundation for other scientists to keep exploring those big questions.
Definitely. And his work keeps inspiring new research, pushing the boundaries of what we know about the brain and how it creates all of human experience.
This has been an amazing journey. We've covered so much, from those basic principles of Hebbian learning to how it's shaping the future of neuroscience and AI.
It's been great exploring it all with you. And the amazing thing is that even after all these years, Hebb's work is still so relevant. His insights into how the brain learns and adapts, that's still inspiring and challenging us today.
It really reminds you that even when dealing with something as complex as the brain, sometimes the most powerful ideas are the simplest. And as we keep trying to unravel the mysteries of the brain, I think Hebb's legacy will keep guiding us, inspiring new discoveries, helping us push the limits of human knowledge.
Yeah, I think you're right. And to our listener, keep exploring the world of neuroscience and cognitive science. There's a whole universe of fascinating insights out there waiting to be discovered. And who knows, maybe you'll be the one to make that next breakthrough.
Keep those brains active, everyone. And until next time, happy learning.